Hello. Here we will talk about primitive roots modulo a prime. So we'll start with a prime number p, and we'll be looking at, well, effectively the multiplicative group of integers modulo p. And in the terms of group theory, we will be proving that this is cyclic. That is generated by a single element, that is, all integers mod p are non-zero. Integers mod p are powers of a fixed one, and that such integer is called a primitive root. So that primitive root will have all powers different, starting from the zeroth power and up to p minus first power, and that is to have the multiplicative order mod p equal to p minus 1. So that's what we're going to argue, and we will use group theory characterization of cyclic groups, which really says that a group is cyclic, or this particular group is cyclic, if when we solve equations of this form, some power equals 1, and the number of solutions will be bounded by the degree of the equation. So that is kind of equation characterization of cyclic groups. Only works for cyclic groups and only for them. So that is what we can see happening because of the following sort of general behavior of polynomials. So we have to really look at this set as a set of polynomial solutions, roots of a polynomial computed in integers mod p, and the polynomial, of course, is x to the k minus 1. And the key fact here is that p is a prime, and that the integers mod p are so integers mod p form a field. Here I'm assuming I have a generic sort of arbitrary field. So what is to be a field is to have 4 arithmetic operations: addition, subtraction, multiplication and division working in coherent fashion like we have in integers mod p. What is a key property? What I'm using these conditions for the operations is that if I have any polynomial with coefficients in this field, then I can be sure that the number of roots of this polynomial will be bounded by the degree. So again, I'm looking at elements of my field, scalars, which solve this polynomial equation, and then I can be sure that the number of such solutions will not be bigger than the degree of the polynomial, and the degree, of course, is the highest monomial, highest power of t appearing in the polynomial. So that in turn follows from the effectively Euclid's division, but the statement is usually called Bézout's lemma or theorem. And this statement says that if we take a polynomial, and then if we have all 4 arithmetic operations working on its coefficients, we can divide by it by any polynomial and get a remainder, just as Euclid's division works with integers. So if we take a monomial, so if we take a linear polynomial t minus some number and divide by it, then Euclid's division statement would say that we have to have a quotient and then a remainder. So what is this? Let me rewrite it again. Here it's going to be the statement. What is the remainder in general? What should I expect for my remainder? Well, it has to be a polynomial in degree less than what I divide by, so in degree less than 1. There's only one possible degree for such is 0, so that it has to be a number. That is an element of my scalars. And now I just can be sure that this number is nothing but the value of the polynomial on the constant I divide by. Because if I take this equation and I know that this is a number, I can compute it by substituting c instead of my variable. So that is t as well. T is everywhere. Substituting c, the number c, in place of all the variable appearance. So here I'll have 0. On this side I will have the value, and so it should coincide with this number. That's why the Bezoos theorem. And now if we are counting roots, each time we have a root, we can take this as a root, and so that remainder will be 0, and we'll have the factorization statement that each time we have a root, t minus that root can be factored of our polynomial. And we can do it one by one with each of the roots, so that, say, assuming that it is the first root, we factor it out. Then if we have another root, it has to be now the root of g, and we factor out. But each time we factor out, we decrease the degree by 1, so the degree of g is 1 less than the degree of f. So factoring roots one by one, we should stop when we run out of the degree. That's why the bound for the number of roots, the number should not be larger than the degree. So applied here, we have this inequality, and that fits well in the characterization of cyclic groups, guaranteeing that this group is cyclic. Hence we have, no matter what, we should have an element of maximal possible order, of the maximal possible order predicted by the Fermat's-Little theorem. So just to generalize this statement, this is the statement proved here. Just to generalize this statement, we could say that if we have a field again and look at the multiplicative group of non-zero elements and look at some subgroup in here of finite order, then we can be sure that this subgroup is cyclic. And the logic is still the same, so we look at the characterization of cyclic groups, we apply to this group the characterization of cyclic groups, we look at the subset of solutions inside this group of this equation, and then we know by the same argument that these are roots of the polynomial of degree k, so the number of such should be bounded by k, and that is enough to be sure that the group is cyclic. So again, that is the same logic. Let me complete by looking at an example, or a couple of examples. So really it's just to show that the condition that p is a prime is to be taken seriously. So if we say take, instead of prime p, take a composite number like 24, then for any integer mod 24, the square will be congruent to 1. And the maximal possible order for, or the size of the group rather the order of the group, is of course the oldest function of 24, which is the oldest function of prime decomposition of 24, which is 2 cubed times 3. So that will be 4 times 2 will be 8. We have 8 invertible numbers, mod 24. So the group is of order 8, but all elements are of order at most 2. It's not cyclic, of course. But yes, at the same time, there are composite P's which still work for that statement. So they're, say, take integers mod 9 and look at this group. And the order of this group, of course, is the oldest function of 9, which is 6. And there is an integer with the multiplicative for the mod 9 being 6. Take 2. So 2 cubed, 2 squared is not 1. 2 cubed is not 1, because it's 8 mod 9, it's negative 1. So it has to be 6 that is the order of 2, because the order of 2 has to be divisor of 6 by Lagrange's theorem, and the only possibilities 1, 2, 3 and 6. So that is a primitive root modulo 6, although 6, primitive root modulo 9, although 9 is a composite number. So the general story is covered by the Gauss's theorem. We'll probably discuss it sometime later.